This is the next video in the chapter on electronic structure and periodic properties. We are finally going to talk about periodic properties. We are going to talk about atomic radius, ionization energy, and electron affinity. So we just finished talking about the periodic table in the last video and how it's organized by chemical properties. So we said that elements in a group, which is what we call the vertical columns, elements in a group share chemical properties. We organize them that way on purpose. And the reason they share similar properties is because of their electron configurations. Specifically, the valence electron configuration. Remember, those are the only electrons we care about, the ones that are in the outermost shell. The valence electron configurations of elements in the same group are the same. And this valence electron configurations, another word for this is valency. You might hear someone call it that. So, same group, same chemical properties, same valency. Here's an example. We talked about the lithium, sodium, potassium family, the alkali metals before. So lithium has 3 electrons. Here it is in the table, it's the third one. So the 1s orbital is filled and there's a first electron in the 2s orbital. So instead of writing 1s, we can use the noble gas shorthand configuration and just write helium to summarize the core electrons and 2s1 for the others. Sodium is the next one down with 11 electrons. Right here, it's the first one in period 3, and so it is the first one after this noble gas neon. So its electron configuration is neon 3s1, and potassium with 19 electrons is the first one in row 4, and it comes right after the last noble gas in row 3, which was argon. So we can write it as argon 4s1. And you can see the advantage of using the shorthand notation because we can see we've emphasized the similarities between these elements. Remember that everything that's outside of the noble gas bracket, those are the valence electrons. And so the valency for these 3 atoms is the same. They all have the outermost shell, s orbital has a single electron in it. So this is a periodic trend. And there are more periodic trends that we'll talk about now. Never knew how useful the periodic table could be. So those periodic trends are here: the radius, the ionization energy, and the electron affinity. So we will start with the atomic radius because that's the best one to start talking about. And here's the trend over here. The atomic radius is going to be a positive number. And the most positive number is towards the bottom and towards the left side of the periodic table. So how do we define the radius? That's a first question that we need to ask. So an atom is roughly spherical and the nucleus is in the center. So the radius would simply be the distance from the nucleus to the outer edge. But because this is not an actual sphere with a hard outer edge like a ball, we cannot simply hold up a measuring tape to an atom to find out how far it is from the center to the outside. And also, we don't exactly have a hard outer barrier here. We're defining the edge of an atom as the furthest electron from the nucleus. And as you remember in the quantum section, The electron, we don't have a specific measurement for its location. It's constantly moving and it's constantly changing position. And all we have is an outermost outline of the volume where it has a 90% chance of being. So it's sort of difficult to figure out where it is. So that we measure a radius that's sort of easy to experimentally measure, and that is a terrible circle, so terrible that I'm going to change where the nucleus is. So the easiest way for us to measure the radius is to form a covalent compound with two of the same atom. And to measure the distance between the nuclei and to divide that number in half to get the radius. So the distance between the two nuclei is 2 times r. And so half of that is going to be our radius. That is going to be how we define it. Here is a picture from the textbook that demonstrates that. So we have 2 atoms of the same element that are connected together. If we measure the distance between the 2 nuclei and we divide that by 2, that gives us the radius. So how do we find out what this trend is vertically and horizontally in the table? How can we predict whether the radius is going to increase or decrease? Here's what we know. As we move down a group in the table, those atoms are getting significantly bigger. We're adding a huge chunk of protons, and for every proton, we're adding an electron so that they stay neutral. So as we move down, we are adding more protons to the nucleus. And the same number of electrons to the electron cloud, so that every atom is still neutral. And these protons and electrons and their relative numbers and position are going to tell us how large that atom is going to be. We're specifically interested in the electrons in this moment. So what happens when we add that next electron? Where does it go? What orbital does that live in? As we add the new electrons, they fill the larger orbitals, right? As the Aufbau principle tells us that we fill electrons from the smaller principal quantum number orbitals to the larger principal quantum numbers. And those larger principal quantum numbers are physically larger, and they are farther away from the nucleus. So the electrons here, each additional electron lives farther from the nucleus than the last. So we might have the 1s orbital, the electrons live pretty close to the nucleus. And then as we move to the 2s orbital, the electrons are a little bit farther from the nucleus. And once we start filling the 3s orbital, those electrons are significantly farther away from the nucleus than those earlier ones. And being farther away from the nucleus means that the radius is going to be larger. So that tells us about our vertical trend. So our radius increases as we move down a group. So the increasing direction is down, and that's why we drew the arrow pointing down in the table. So we can rationalize that. That makes sense. We add more electrons, they're farther away, so the radius is larger. So is this also true moving across a period? Because we know as we step across a period, each step involves the addition of one more proton and one more electron. So could that trend still be true? That's what we would predict. But the answer is no. That trend is not true. So in the next video, we will talk about moving across a period and how to understand that trend in atomic radius.